Здравствуйте.
Так, добрый день. Давайте я начинаю лекцию. Today I will explain you what are the so-called LDPC codes. So this abbreviation means low density parity check codes. So these are binary codes, and they are some alternative to Fortnite codes. So their parameters lie somewhere here, strictly below the Gilbert line. And what's more important, they are bounded away from zero, from both axes. So they are rate and relative distance are bounded away from zero. Frankly speaking, their parameters are worse than those of Fortnite codes, but on the bright side, the decoding algorithm is much simpler. So the idea of such code first was developed by Gallagher in 1950s, and then people almost forgot about those codes, and the idea was revived by Sipser and who? Let me check. And Spielman in 90s. They revived the idea because they connected the Gallagher idea with the so-called expander graphs. So what is it? So this will be linear codes with alphabet F2 considered as a field. And every such code may be expressed using system of linear equations over F2. Usually such equations are called parity checks. So that explains part of the title of the name of the codes. So, and we will express those system of linear equations, which defines a set of code words, using the bipartite graph. On the left nodes will be variables of those equations. X1, X2, X3, X4, X5, and so on, Xn. So n is the block length. Each symbol of the code words is understood as variables with two values with the range of 2. And each equation will be represented as a right node. These are equations, linear equations. For example, the equation x1, say, plus x3 plus x5 equals 0 will be expressed by 3 edges of this graph. Each edge connects the equation with one of variables from that equations. For example, this equation is represented by a right node of the bipartite graph, and the edge connects it with x1, x3, and x5. And so this is quite general. Every linear subspace of F2, which has dimension n, can be represented using equations where the number of equations is equal. So call it M equations. And M is equal to n minus the dimension of the code. So we will assume that, so our code will have parameter n minus m, and some distance. However, we will consider very spatial graphs, and we will show that for such graphs, we have large enough minimum distance. So what is this property? It's called expander property. So expander property, expanding property is better to say. Expander property means that if we take certain subset of the set of left nodes and consider all its neighbors, then the number of neighbors is close to the maximum possible. So first of all, what is maximum possible? We will assume that every left node has fixed degree, say d. So this is left nodes, and then we will assume that each left nodes has exactly d neighbors. So this means, in other words, our graph is d-regular from the left. So let me write here the first property of the graph. So every left node has d neighbors. In other words, every left node appears in exactly d equations. And the second property is called expanding property. This property has some parameter, epsilon, actually 2 parameters. And the property is the following one. So let's call the set of left nodes capital L, the set of right nodes capital R. So L is the set of variables, R is the set of equations. And the property is that for all subsets R, A of R, L, if A has at most certain number k nodes, so k is the first parameters, then the set of all neighbors, call it gamma of A. So gamma of A by definition is all the neighbors of A is large enough. More precisely, it's almost close to the maximal possible. So maximal possible number of neighbors is cardinality of A times D, because each node has D neighbors, and so in total they might have D times cardinality of A neighbors. So, and the requirement will be that the number of neighbors is at least larger than 1 minus epsilon of that. And the graphs satisfying 1 and 2 will be called D, K, epsilon expanders, Так, скажите, понятно это определение?
Да.
Ключевое
Ну,
для сегодняшней лекции.
а вот еще раз, можно вот что такое соседи множества А под множеством? Это вот,
Мы берем для каждой вершины всех ее соседей и объединяем
ага,
эти множества по всем вершинам из А.
ага. А вот что вот слева написано, что в А не больше, чем К элементов, да?
Да.
Ага, окей, хорошо.
It's clear that we can't demand that all subsets of L gets expanded, because typically R is less than L. So R is the number of equations. Of course, we want to the number of equations be less than the block length. Otherwise, the rate will be negligible. So typically, the number of equations is certain fraction of the number of variables. So it's impossible that all the sets gets expanded. And we will construct such a graph where K is a certain fraction of N. Say K is 1 over 1,000 times N. So all the sets whose cardinality is much less than N gets expanded, and we do not care what happens with other sets. And so now I will explain two things. First of all, why these expanding properties imply that the distance is, the minimum distance is small. Second, how to decode using a very simple algorithms from errors, and how many errors we can decode using that algorithm. And third, why such graphs, expander graphs, exists at all. So I will start with a certain lemma, and then prove something about minimal distance. So the lemma is the following. We will call, so consider a set A, a subset of L. So A is a subset of L. And we will call certain neighbor, call it, say, this is V, and this is, say, U. And U is called unique neighbor of V. Actually, this depends on A, this definition. So to be more precise, we should say relative to, with respect to A. With respect to A. If U has no other neighbors in A, except for V. So if U has no neighbors in A different from V, And this here is an example. Assume, say, that the picture is like that. Then this U is a unique neighbor. So A has two nodes, this and one and this one. Say this node has another neighbor somewhere here. And U is a unique neighbor with respect to A. This, call it U prime, is also a unique neighbor, but this U prime prime is not a unique neighbor, but because it has two neighbors in A. And lemma states that gamma of A, the set of all, assuming that A has at most k nodes, gamma of A has more than 1 minus 2 epsilon times cardinality of A, unique neighbors, if A has at most k nodes. So, and why is this? So assume that this is R, and this is gamma of A. This circle represents gamma of A. So we know that gamma of A has more than 1 minus epsilon. This implies that gamma of A has more than 1 minus epsilon d. Sorry, here we need to multiply also by d. It's important. Nodes. But look, if we have some non-unique neighbor, then that neighbor, so d times A is obtained if we count the total number of edges. But if some node from the right, from gamma of A, has two incoming edges from A, that means that it decreases gamma of A at least by 1 compared to its maximal number d times A. So if we have more than at least epsilon A non-unique neighbors, then the total number of nodes in gamma of A would be less than 1 minus epsilon times the maximum. So the key point here is that the number of non-unique neighbors of A is less than epsilon times A. Сейчас, вот поняли это ключевое рассуждение? Почему количество неединственных соседей,
Не совсем.
неуединенных соседей строго меньше эпсилон на А?
Не совсем.
Ну, смотрите, каждый неуединенный сосед содержит два ребра. В него входит по крайней мере два ребра. Значит, DA получается, если вообще считать, что все уединенные. Потому что как только у нас какой-то неуединенный, он будет уменьшать максимально возможный размер на единицу. Ну, DA считается, как будто концы всех ребер разные. Как мы можем получить вообще DA соседей? У нас А вершин, у каждого D соседей. Значит, DA получается, если все концы различные. Как только два конца склеиваются, это уменьшает максимум на единицу. Значит, если бы у нас k was больше, чем эпсилон А, то, соответственно, максимум уменьшился бы на эпсилон А.
Ну, хорошо, тогда нужно в, в количестве писать эпсилон А на D.
Ну, на D, да, точно.
Ну, хорошо. Ага.
Okay. The number of non-unique neighbors of A is at most epsilon times A times D. And the total number of neighbors is, by definition, by expanding property, 1 minus epsilon dA. We just subtract from this bound, and we are done. So actually, this inequality is non-strict one, or maybe even strict. It doesn't matter anyway. So we subtract from the total number of neighbors from gamma of A the number of non-unique neighbors, and we obtain the number of unique neighbors. And so it's more than 1 minus 2 epsilon times A times D. Okay, so the lemma is proved. And later we will assume that epsilon is at most 1/4 or at most 1/2. And this implies that under the assumption that A has at most k nodes, gamma of A has at least one unique neighbor. So the second lemma states that if epsilon is at most 1/2, then the code we construct, the code defined by that number, has minimum distance larger than alpha times n. Wait. What is alpha? I denoted it by k, sorry. Is larger than k. Is larger than k. So how to prove it? First of all, we know that for linear codes, minimum distance is the minimum possible Hamming weight of non-zero vector. So assume that we have some code word, non-zero code words. Assume that we have some code words which has at most k1s of Hamming weight, at most k. Then consider A to be equal to the set of all positions where xi is 1. So we know that A has at most k nodes, and hence by our lemma, gamma of A has more than 1 minus 2 epsilon times A, which is positive, actually which is non-negative, because epsilon is at most 1/2. Unique neighbors. And the point is that recall that neighbors represent equations, and unique neighbors represent equations that includes only exactly one variable from A. And other variables from that equation do not belong to A, and hence they are 0. So each unique neighbor is equation that has exactly one, and hence that equation is wrong. The equation, its left-hand side is 1, and the equation is it's a homogeneous equation, all our equations are homogeneous, and the left-hand side includes only one variable from A. So the equation is wrong. Such equations will be just called wrong. So, and every unique neighbor is a wrong equation. So that contradicts the assumption that X is a code word, because all the code words satisfy all parity checksums. Так, ну что, понятно это рассуждение?
Да.
Good. So the first item is finished. I have explained that the minimum distance is actually larger than k. So I can now replace this question mark by k plus 1. Actually, if epsilon is very small, we can increase this, prove that the distance is larger than k plus 1 by some other arguments, but I will skip it now, at least now. So this was the first thing I wanted to explain. And now the second thing, how to decode from errors. How to decode. We will decode from k almost as, so recall that if the distance is k plus 1, we can decode from k over 2 errors. So we will decode, I guess, from k minus 1 over 2 errors. So the algorithm is the following. So the input, our input is some corrupted code word tilde_x. Now we have one large loop while loop. So first of all, we compute all parity checksums. So we evaluate all the equations, and we loop until there is at least one wrong equation. While there are a wrong equation, we try to flip one bit of x tilde x. And if flipping that bit decreases the number of wrong equations, we just flip that bit. So the idea is to decrease the number of wrong equations until it becomes 0. Pick I such that flipping tilde xi decreases the number of wrong equations. We will show that there is such bit. And second, we just flip that bit, decreasing the number of wrong equations. And this is the end of while loop. And after that, we will obtain some code word, and we will prove that this is actually the code word we were looking for. More precisely, we will prove that the distance between the initial code word and the resulting code word is at most k. And we know that the distance between different code words are larger than k, so that means that our code word is the code word we were looking for. Так, понятен алгоритм? Ну, конечно, по модулю того, что мне еще надо доказать, что такое и существует всегда.
Понятен.
Okay. Now, first, let's show that such A exists, at least on the first step. Actually, to prove that such A exists, well, let's see what we will need, but let's show that that at least it exists on the first step. And here we will assume that epsilon is at most 1/4. So 1/4, we need a little bit smaller upper bound for epsilon. So if epsilon is at most 1/4, then, and also we assume that the number of errors is at most k minus 1/2. And let's introduce some notation. We will denote by A the number, the set of all positions where the corrupted word is different. The corrupted code word is different from the genuine one. So X is the genuine one. So X is the code word is the transmitted code word. And tilde X is different from X, but we know that the Hamming distance between X and tilde X is at most k minus 1/2. So in other words, we know that the cardinality of A is at most k minus 1/2. So if epsilon is at most 1/2 and okay, let's write it later. What are the requirements about A or whatever we need? Then there is such I. So we want to prove that there is such I under certain assumptions, and we will figure out what assumption we need later. So what do we, so first of all, we need the assumption that A is at most K. Under that assumption, we know that gamma of A has more than 1 minus 2 epsilon times dA unique neighbors. This is one of our lemmas. And given the assumption about epsilon, that it is actually this inequality is strict, and the given assumption about epsilon, so epsilon is not 1/4, 1/4, we know that this is at least dA over 2. So gamma has larger than dA over 2 unique neighbors. And that implies that there is a node in A such that V has more than D over 2 unique neighbors. So some node in A has more than D over 2 unique neighbors. And why is this? So we know that the total number of unique neighbors is at most is larger than D over A over 2. This number may be obtained by just summing. At least it's at most the sum over all nodes in V, in A, of the number of unique neighbors of that node. So at least one term in that sum should be larger than D over 2. Otherwise, the sum couldn't be larger than D over 2 times the number of terms. So this is sort of obvious. And note that if V has larger than D over 2 unique neighbors, then flipping that variable, flipping some variable will change all the checksums where it appears. And it will correct all the sums of the wrong sum where it appears. But we know that each unique neighbor is actually a wrong sum because it, so recall that A is a number of, A is a set of variables where our code word is different from tilde x. So each variable in A is sort of a wrong variable. It's an error. And so because our equations are linear equations, and if we change all the variables which are all the variables which are, so how to explain it? So for each equation, say f of x is 0, if we know that xi so tilde f of tilde x is actually 0, which is f at x, plus the sum over all i's better to say is 0, which is f at x, plus f of tilde x minus x. And if we know that certain equation f has exactly one variable from A, that we know that this guy is exactly one. And so this requires that flipping v, the variable v, in tilde x, meaning tilde x, will correct more than d over 2 unique checksums equations. And it can that variable appears in exactly d equations, and so the number of equations which were spoiled by flipping that variable is less than d over 2, because flipping that variable changes all the equations in which it appears, and among them more than half are wrong. So flipping that variable corrects more than equations than it spoils. And so, in total, the number of wrong equations decreases. Так, понятно это?
Да.
Okay, so now we see what actually another assumption. We need that A is has at most K variables. So if epsilon is most 1/2, and the number of wrong variables where our code words is different from I is at most K, then there is such I. So of course, on the first step, this equality is wrong. We know that even the number of equations of wrong variables is even less than K over 2. But later, A can actually increase. And why is this? It might happen. So in the proof of the lemma, we showed that there is at least one wrong variables, flipping which we decrease the number of wrong equations. However, in the first, in this, on this step, we do not know actually which i's are wrong and which are right. So it might happen that also changing some good variables decreases the number of wrong equations. And so during our loop, the cardinality of A might increase. And so somehow we need to prove that it never becomes larger than K. And the other thing we need to prove is that finally, when the number of wrong equations becomes 0, the resulting code word is different from the genuine code word in at most K positions. And to prove both things, we need to find some invariant, some statement which is invariant under performance steps 1 and 2. And so we will prove the following lemma. After each loop and before each loop, we have two things. First, A has at most K nodes. So A changes from steps to step because we change tilde x, so we change A. And the second thing, the number of wrong sums or wrong equations. I mean for the current version of tilde x is at most k minus 1 over 2 times d. After and before. So first of all, let's check that it's true at the very beginning. At the very beginning, we know that A is even at most k minus 1 over 2. And so this inequality holds with, it amply holds. And the second requirement holds because the number of wrong variables is at most k minus 1 over 2. And each of them can spoil at least d sums, because the total number of wrong equations is at most the number of wrong variables times d, because each wrong variables appear in d equations. So this is a simple thing. Before the first loop, our invariant holds. Now, second, we need to prove that it holds after each successive loop. And this is done as follows. First of all, these two things imply that A is at most k minus 1, a little bit stronger requirement than we had. And this is because the number of wrong equation is connected to the cardinality of A. So assuming that A is has at most k nodes, we know that the number of wrong equations is at least the number of unique neighbors of A. And this is at least d over 2 times A by one of our lemmas. And on the other hand, we know that the number of wrong equations is at most k minus 1 over 2 times d by the second our assumption. And so you see that this implies that actually A has at most k minus 1 nodes. And so this was before the loop. And in the loop, we change possibly wrong good variables, but changing one variable may increase A only by 1. So this implies that A, cardinality of A, is at most k even after the loop. So you see that knowing that A has at most k nodes and the number of wrong equations at most k minus 1 over 2 times d before the loop implies that actually A is at most k minus 1 before the loop, and that implies that it is at most k after the loop. Good. That means that the number of variables in A is at most k, which is the first part of our environment. And the second part holds because when we change the variable, the number of wrong variables even decreases. So if it were at most that much, then after the loop it becomes even less. So that means that one execution of the loop keeps this statement true. And so by one of our lemma, that means the requirement that capital A is at most has the cardinality of A is most K implies that actually there is a variable flipping which we decrease the number of wrong equations, and that means that our loop terminates after at most K over 2 steps, and we will obtain a certain tilde x for which A is at most K. So that means that the number of wrong positions is at most K. So that means that tilde x differs from the genuine code word is at most K positions. On the other hand, after the execution of the loop, all the checksums for tilde x are good. So all of them are 0. And that means that tilde x is also a code word. And because the minimum distance is larger than K, that means that tilde x we obtain after execution of loop is the genuine code words. And we are done. Ну что, понятно доказательство?
Да.
Хорошо, давайте сейчас перерыв тогда, значит, 57 минут продолжим.
Прошу прощения, вы не включили звук.
Sorry, indeed. So it remains to perform the last step, proving the existence of expanders, expanding graphs. Proving that expander exists. So recall that we need that epsilon is at most 1/4. So the requirement that if A is the set of left nodes and L A is a set of left nodes of cardinality at most K. So L, the parameters are that L is the number of variables, or in other words, the block length, and call it 10. So the number of right nodes, call it M, say, M right nodes. This is number of equations. And the requirement is that every set gets expanded. That means that if A has at most K nodes, then it has at larger than 1 minus epsilon times D times A neighbors. And also there is another requirement that each left node has exactly D neighbors. And we will use a randomized construction. More precisely, randomized arguments. So we will prove that if we take our graph at random, so we fix our parameters n, epsilon. Epsilon will be chosen 1/4, m, and d. So we fix our parameters and see for which parameters with high probability, or at least with positive probability, a random graph satisfies this property, this expanding property. And what means a random graph? That means that for each node, we choose its D neighbors at random. So so in other words, we choose at random a D element subset of the right, the set of right nodes. So we need to upper bound the probability that a random graph doesn't satisfy this expanding property. And we will show that it is less than 1, assuming certain relationship between parameters. So to show this, we need to upper bound this probability, and let's upper bound it as follows. So this event is a sum of events where union of events over all possible A and B, where A has at most K nodes, B has cardinality uh, 1 minus epsilon times D times A, and the event itself means that gamma of A is included in B. I mean here non-strict inclusion, let's try that. So if our graph doesn't satisfy expanding property, then there is a set A of at most K nodes and some set B of exactly that much nodes. such that all neighbors of A are inside B. Понятно это?
Да.
Okay. Now we will rewrite this sum. Summing first for over K. And now this inner sum will be the sum over all A's of cardinality K and B's of cardinality 1 minus epsilon times D times K. And here we need to write down the probability that gamma of A is included in B. Now we just this sum has n choose K terms. The set A can be chosen n choose K times in n choose K possible ways. The set B can be chosen in m choose that much possible ways. And for each choice of A and B, the probability of this event is the probability. What is that probability? The probability when we fix B and A, that means that all the neighbors of each node are included in B. So this probability can be computed exactly because all the nodes are independent. And so we will obtain here at most the number of terms here, which is n choose K, m choose 1 minus epsilon dk. And here is the probability that for a particular node, left node, all its neighbors fall in B. And this is m over B times m minus 1 over B minus 1, and so on. Here we have the product of K fractions. And we need to raise this to the power of K because we have K different nodes in A. So let's rewrite it. Like that. And here, actually, it's not hard to see that the first factor is the largest one. So we can upper bound this by m over B. Recall that B is that much. To the power of, sorry. I need to raise here to the power of K times D because we have, here is my mistake. From each node we have D and not K edges. So this K should be changed to D, both this case. This was my mistake. So D here and D here. And so this product is actually maybe upper bounded by m over B raised to the power of D and then raised to the power of K, so dk. So this is our bound, and we want to simplify it using the bound for n choose K. So n choose K is actually n times n minus 1 and so on, n minus 1 plus K over K factorial. Now, this can be upper bounded as n to the k because n is the largest factor here over k factorial. And for k factorial, we have the following bound. It is at least k over e to the k. If I will have, if I have enough time, I will explain how this can be proven. But for now, let's assume that this is indeed true, and then we will obtain the following upper bound. N e over k raised to the power of k. And so using this upper bound for the binomial coefficient, we can rewrite everything here as follows. So our probability is at most n choose k, which means n e over k to the k. Now m choose 1 minus epsilon times kd times e to the 1 minus epsilon kd. And the last term is m over 1 minus epsilon dk raised to the power of kd. So let me check. This is strange. So yeah, I confused something. А почему вы меня это самое совсем не оборвали? Вот здесь я уже написал глупость. Это же была вероятность, а я пишу m делить на мощность b. Мощность b, она вообще меньше m. Здесь все надо перевернуть, естественно. Значит, какова вероятность того, что если мы выбираем случайно подмножество из d вершин в m-элементном множестве, то все они попадут в b. Первая вершина попадает в b с вероятностью мощность b делить на m. После этого вторая вершина выбирается среди отличных от первой из b, то есть b минус 1, а всего вариантов m минус 1. То есть здесь все надо перевернуть. Я написал глупость, а вы уж прямо это самое совсем не следите. Окей. Here we need to write b over m times b minus 1 over m minus 1 and so on. So again, here, instead of that, we need to write down m over 1 minus epsilon dk. So here, we also need to change the numerator and denominator. So m 1 minus epsilon dk. Так, понятно это? Посмотрите внимательно.
Ну, вроде да.
Ну, вообще, я вижу, что уже невозможно следить, конечно. Ну, ладно, поверьте, что вот это так. Значит, Okay, and this can be simplified. First of all, one can see that everything is raised to the power of k. So we can, first of all, we can rewrite this as follows. Raise everything k and write down that we just raise everything to the power of k. And recall that this is only one term, and actually we had the sum of such terms, the sum over all k's of this. So this can be, so this should be corrected, writing down that actually we have a sum over all k's from 1 to n of this. And now we will choose our parameters so that this guy is at most 1/2. Once we know that this is at most 1/2, we know that our sum is actually at most the sum of geometric progression with the ratio 1/2. And this means that the sum of the whole progression of infinite progression with that ratio is 1. So our partial sum will be strictly less than 1. So this is our goal. We want to show, we wish this, that this is at most 1/2. So let's see how we can simplify this thing. First of all, we can cancel here m over 1 minus epsilon kd to the power of d, because we have here and here the same thing. So this thing may be simplified as n e over k times e to the power 1 minus epsilon d, and times 1 minus epsilon k d over m to the power of epsilon d. And now we can choose the parameters. So choose, say, epsilon 1/4, choose d, say 5, and then we see that this becomes 5, and so k is raised to the power of 5 here, 5/4 here, and here to the power of only 1. So that means that this guy decreases when k increases, and so increases, not decreases. And so its largest value is when k is equal to there is a variables collision. So our k is actually should be replaced by some other letter, say I, because k is actually used as the upper bound for, so for that k. So let's rewrite this k, everything, say by I. So I ranges from 1 to k, because largest possible cardinality of I is k. So I here, I here, I here, and also I here, and I here. And so we know that I is at most k, and for these values of d and epsilon, this guy increases when I increases, and so this is at most n epsilon e over k. So the maximal possible value of I is k. So let's replace this just by d for simplicity. Let's replace here also by d. So we obtain kd over m to the power of 5/4. And now we see how we can choose our parameters. So we have already chosen d is 5, so here we can also replace by 5. So we need that be less than 1/2. And to this end, we can choose first. So assume that we are given n. So n is given. Some number. So this is the block length. Then we can choose the rate of our code arbitrarily. So we assume that also m is given. The rate of our code is n minus the number of equations, which is dimension, over n. So assume that n is given and also m is given. Then the only thing we can choose is k. But the point is that this thing decreases when k decreases. So we can choose k proportional to, then we choose k over n. More specifically, assume that n is given, m is given, and the rate of our code is certain fixed number, call it beta, is fixed. Then all the ratios n over m is fixed. And choosing k over n small enough, so let's rewrite it using now we want to choose k over n, call it alpha, small enough. And if k over n is small enough, we will obtain that this is at most 1/2. Let's see why is this. So our m, this m is beta n minus beta n. Let's write it here. N times 1 minus beta. And you see that as a function of k over n, this value increases when k over n increases, because we have here k over n to the power of -1 and here to the power of 5/4. So as a function of k over n, this is some constant raised to the power of 1/4. And so if we choose alpha small enough, this will become less than 1/2. And so the choices of parameters is the following one. We fix some beta, the rate of our code, n is given to us, which is large enough, and given the rate, we can choose alpha, which is the relative distance of our code, small enough, so this is at most 1/2. More specifically, one can show that we can choose the following parameters. So more precisely, we can choose k, so the rate, we can choose the rate equal, say, to 0.17, and the relative distance then will be very small, actually, 1/2050. And this technique allows to construct only the codes whose relative distance is very small. Something like that. Так, ладно, давайте теперь вам дам тест. Сейчас. Так, тест очень простой. 10 минут должно хватить. Значит, 38 минут. Закончим.